Okay, we're going to start chapter 4 now. In chapter 2, we discussed motion in one dimension. In chapter 3, we discussed vectors. So in chapter 4, we marry those two concepts, and we're going to discuss motion in two dimensions, and we're going to use vectors to describe it. That's why we started with the intro of motion in one dimension, so you can get used to those ideas of position, acceleration, and velocity. And then we studied vectors. Now we can combine the two and study motion in two dimensions. We're going to talk about two types of two-dimensional motion: projectile motion, which is such as the path of a thrown baseball or football, a little ball-bearing pellet shot from a small cannon. We're going to do that in the projectile motion lab. We're also going to discuss circular motion, such as the idealized motion of a planet around a star. And then we're going to discuss the concept of relative motion, which shows why observers in different frames of references may measure different positions and velocities for a given particle. It depends on your frame of reference. I'm also going to recommend a little video. It's an old video, but it very well describes the frames of reference. Now let's get going with the lecture. The slide says position vector. In one dimension, a single numerical value describes a particle's position. In two dimensions, the position is indicated by a position vector r. It's drawn from the origin of a coordinate system to a location, the location of the particle in the xy plane, such as the figure shows there. At time t initial, the particle is at point A and is described by the position vector r initial. At later time, t final, it's at point B and is described by a position vector r final. The path followed by the particle from A to B is not necessarily a straight line. As the particle moves from A to B in time interval delta t, the position vector changes from r initial to r final. The displacement is a vector. The displacement of the particle between the final and initial positions is a vector. We define the displacement vector delta r for the particle as the difference between the final position vector and the initial position vector, as shown here. So delta r is equal to r final minus r initial. So the direction of delta r is indicated in the figure, and the magnitude of r is less than the distance traveled along the curved path followed by the particle. Okay, let's, oops, wrong button. There we go. Now, it's often useful to quantify motion by looking at displacement divided by the time interval during which that displacement occurs. The rate of change of position. So the change of position over time will be what? It'll be velocity. So in two-dimensional or three-dimensional kinematics, it's similar to one-dimensional kinematics. We must now use full vector notation rather than positive and negative signs to indicate direction of motion. So the average velocity, V average, of a particle during the time interval delta t is the displacement of the particle divided by the time interval. So V average is equal to delta r divided by delta t. Now notice here, V average is equal to, V average is a vector and delta r is a vector. Delta t is just a scalar, since time isn't a vector quantity. Now, notice also that since delta t is just a scalar quantity, V average has to point in the same direction as delta r. Okay. Now, the average velocity between points is independent of the path taken. The average velocity is proportional to the displacement. It depends only on the initial and final position vectors, not on the path taken. The particle starts motion at some point and returns to this point via any path, then the average velocity is zero because the displacement is equal to zero. We've discussed that in one-dimensional motion. So consider the motion of a particle between 2 points in the xy plane, as shown in the figure. The dashed curve shows the path of the particle. As the time interval becomes smaller and smaller, as b moves from as b is moved to b prime, and then to b double prime, etc., the direction of displacement approaches the green line tangent to the path at A. The instantaneous velocity, v, is defined as the limit of average velocity, delta r over delta t, as t approaches zero. So the instantaneous velocity, not average velocity, the instantaneous velocity is the limit as delta t approaches zero of delta r over delta t. In calculus notation, it's dr dt. This is a calculus-based physics course, so you have to know these this nomenclature, dr dt. The instantaneous velocity is the derivative of the position vector with respect to time. The direction of the instantaneous velocity vector at any point in a particle's path along a line tangent to the path at that point, and it is the line tangent at that point, and it's in the direction of motion. Okay, the magnitude of the instantaneous velocity vector of a particle, v, is the absolute value of v vector. I think I've been using that symbol in solving some problems, and that becomes the speed of the particle. It's no longer a vector. Okay, the acceleration, as a particle moves from one point to another along some path, the instantaneous velocity vector changes from vi at time ti, in other words, v initial at time t initial, to v final at time t final. Knowing the velocity at these points, we can determine the average acceleration of a particle. The average acceleration is the change in instantaneous velocity vector, delta v, divided by the time interval, delta t, during which that change occurs. So the average acceleration is delta v over delta t. It's a change in velocity over time. Okay, so the A average is the ratio of vector quantity delta v and positive scalar quantity delta t. So average acceleration is equal to the vector quantity directed along delta v. Remember, you've got one vector divided by a scalar, so you're going to get another vector in the same direction. Instantaneous direct acceleration is the limiting value of the ratio delta v over delta t as delta t approaches zero. So there's the instantaneous acceleration is the limit as delta t approaches zero of delta v over delta t, or dv dt in calculus terms. So the instantaneous acceleration is the time derivative of the velocity vector. Okay, let's take a quick quiz. Consider the following controls in an automobile in motion: the gas pedal, the brake, and the steering wheel. What are the controls in this list that cause an acceleration of the car? Is it all three controls, the gas pedal and the brake, only the brake, only the gas pedal, only the steering wheel? Well, think about it, and you should know these, right? It's all three controls. It's all three controls. The gas pedal will make the car go faster. The brake will make the car slow down, and the steering wheel will change its direction. And all of those are an acceleration of the vehicle. Okay, this ends our discussion of section 4.1. We will continue with section 4.2 two-dimensional motion with constant acceleration. All right.